You think you know the planet Uranus. You are almost certainly wrong. It is not a bland, blue marble lost in the outer dark, but a world of profound and bizarre mysteries. This is the ice giant that spins completely on its side, a cosmic oddball harboring secrets from its chaotic atmosphere to its enigmatic, fractured moons. By the end of this journey, you will see our solar system in a startling new light through the lens of its strangest world. We will uncover why it radiates almost no heat, how diamond rain might fall inside it, and what shattered one of its moons into a jigsaw puzzle. What does it truly mean for a world to be alien? This world does not spin like any other. While Earth and its siblings twirl with their poles pointing roughly up and down, Uranus performs a cosmic somersault, rolling around the Sun on its side. Its axis is tilted a staggering 98 degrees, meaning its north pole points almost directly at the Sun during its solstice. For a quarter of its 84-year orbit, one entire hemisphere basks in constant daylight while the other endures a decades-long frigid night. The question is not just why this happened, but how anything could knock a planet so completely off kilter. The leading explanation is as dramatic as it sounds. Astronomers suspect that in the solar system's violent youth, a protoplanet perhaps twice the size of Earth smashed directly into Uranus. This was not a glancing blow, but a cataclysmic, head-on collision powerful enough to knock the entire world sideways. You can picture the aftermath, a molten, reeling giant, its rotation forever altered by a single moment of cosmic violence. It is a clean, compelling story, one that fits with our understanding of how chaotic the early solar system was. But like so many things with Uranus, the evidence complicates this neat narrative. The problem lies with its family. Uranus has 27 known moons, and they all orbit in the same bizarre, tilted plane as the planet's equator. If a single massive impact had knocked Uranus sideways after its moons had formed, we would expect the moons to be orbiting in their original, upright paths, like a spinning top that gets bumped but whose surrounding specks of dust keep their old trajectories. The fact that the entire Uranian system, planet and moons together, is tilted as one unit suggests the tilt happened very early, before the moons coalesced from the debris disk that would have surrounded the infant, wounded planet. This forces scientists to reconsider the timeline and the mechanism. Could it have been a different kind of gravitational dance? Some theories propose that a series of smaller, but still significant, impacts over time gradually pushed the planet over, a process that would have allowed the moon system to form in the new, tilted orientation. Others suggest a gravitational tug-of-war with a massive, passing protoplanet that never actually collided, but whose immense gravity slowly, over millions of years, pulled Uranus onto its side like a cosmic hand tipping a gyroscope. Each theory has its own challenges, its own mathematical hurdles to clear. The truth is, we are left staring at a solar system oddity with no definitive answer, a world forever frozen in the aftermath of a primeval catastrophe we can only reconstruct in simulations. This extreme tilt is not just a curious fact, it is the foundational mystery that dictates almost every other strange behavior we observe, starting with its utterly bizarre seasons. That extreme tilt creates a seasonal cycle beyond human comprehension. For 21 Earth years, one pole faces the Sun in a single, endless day. Then, for the next 21 years, that same pole plunges into a darkness so profound and prolonged it makes an Arctic winter seem like a brief afternoon. This leads directly to another, deeper mystery, one that defies everything we know about giant planets. Uranus is shockingly, unnervingly cold. While all the other giant planets, Jupiter, Saturn, and even its twin Neptune, radiate more heat from their interiors than they receive from the distant Sun, Uranus does not. It is a cosmic anomaly, a planet that appears to have simply shut down its internal furnace. Thermal images tell a stark story. Jupiter and Saturn glow with fierce infrared energy, their internal heat driving titanic storms and complex cloud bands. Uranus, by contrast, is a faint, cool silhouette. It gives back almost exactly the same amount of energy as it absorbs from sunlight, as if its core has gone silent. This missing heat has profound consequences for its atmosphere. Without that internal engine churning from below, the weather on Uranus, at least compared to its violent siblings, is eerily subdued. It lacks the raging, centuries-old storms of Jupiter or the supersonic winds of Neptune. Its atmosphere is a deep, featureless blue, a calm veneer over a profound thermodynamic mystery. So what happened to its heat? The leading theory circles back to that ancient catastrophe. The same colossal impact that may have knocked Uranus sideways could have also blasted away much of its primordial heat, essentially scrambling its internal structure and allowing its warm core to cool rapidly into a state of deep freeze. Another possibility is even stranger. Uranus might have a unique internal layering that acts like a perfect insulator. Imagine a thermos flask in space. If the layers of slushy, supersonic water and ammonia inside the planet are arranged just so, they could prevent the slow, steady seepage of heat from the core to the upper atmosphere, trapping the warmth deep within where our instruments cannot detect it. This leaves us with a haunting question. Is Uranus a planet still reeling from a single, defining trauma, its heat stolen in an instant? Or is it built differently from the very beginning, a world with a fundamental design flaw in its cosmic plumbing? The cold quiet we see may be the lingering echo of a collision or the signature of a structure we do not yet understand. This profound cold and quiet is just the surface, however. To find the planet's true strangeness, we must look beneath the visible clouds to a force field that defies all logic. Uranus possesses the most chaotic, off-kilter magnetic field in our entire solar system. On Earth, our magnetic field is relatively orderly. Picture a simple bar magnet running through the planet's core, its north and south poles aligning roughly with our geographic poles. This creates the familiar, symmetrical dipole that guides compasses and shields us from solar radiation. Uranus laughs at this simplicity. Its magnetic field is not centered on the planet's core. Instead, it is generated far off to one side, as if the planet's internal dynamo is broken or built on a severe slant. The magnetic poles are nowhere near the geographic poles. In fact, the entire field is tilted about 60 degrees from the planet's axis of rotation. This means a compass on Uranus would point to a magnetic south pole located near its equator, a concept that renders navigation utterly meaningless. But the weirdness does not stop there. Because the magnetic field is so lopsided and off-center, it does not form a neat, symmetrical bubble around the planet. Instead, it resembles a tangled, wobbling mess. As Uranus rotates on its side, this skewed magnetic field gets dragged through space like a poorly thrown football, spiraling and wobbling with every 17-hour day. Solar wind particles do not encounter a smooth, protective shield. They slam into a magnetic field that is corkscrewing wildly, creating auroras that flicker in chaotic, unpredictable patterns far from the poles. So what could possibly generate such an asymmetric, drunken magnetic field? The answer likely lies in a layer deep within the ice giant, in a state of matter so extreme it is like nothing on Earth. Scientists believe that beneath the crushing pressures inside Uranus, water and ammonia do not exist as liquid or ice as we know them. They transform into what is called supersonic ice. In this exotic material, oxygen atoms are locked into a rigid crystalline lattice, like the skeleton of an ice cube, while hydrogen ions flow freely through it like a liquid metal. This creates a strange, electrically conductive slush that can generate magnetic fields, but because it is not a uniformly rotating, metallic core like Earth's, the field it produces is messy, unstable, and wildly off-center. It is as if the planet's internal dynamo is not a solid spinning ball, but a churning, lopsided ocean of exotic matter. This bizarre magnetic field is not just a curiosity, it is a direct window into the alien interior of a world built from ingredients under pressures we can scarcely replicate. And if the planet's core is this strange, what does that mean for the objects caught in its gravitational and magnetic grip? The answer lies in a collection of shattered worlds, the most fractured family of moons in the solar system. These fractured moons orbit within a system of boundaries so delicate they are almost invisible. Uranus is encircled by 13 distinct rings, but calling them rings in the traditional sense is generous. Unlike Saturn's brilliant, icy bands, the rings of Uranus are dark, narrow, and faint, the ghostly traces of a vanished structure. They are composed not of pristine ice, but of material as black as charcoal, some of the least reflective matter in our entire solar system. The leading theory suggests they are made of water ice, but ice that has been utterly transformed. Bathed for eons in the intense radiation belts trapped by that lopsided magnetic field, ordinary ice undergoes a profound chemical change. The radiation bombards the frozen particles, breaking apart molecules and forging new ones, creating a thick, dark sludge of complex organic compounds and carbon, a tar-like coating that absorbs almost all light. This explains their shadowy appearance, but not their precise, thread-like form. These are not wide, diffuse bands, they are razor-thin lines etched around the planet. The Epsilon ring, the brightest and outermost of the set, is only a few dozen miles wide but over 30,000 miles in diameter, a cosmic pencil line drawn with impossible precision. Such sharp edges in nature demand an explanation, and astronomers believe they are sculpted by tiny, unseen guardians. Embedded within the ring system are likely several small shepherd moons, their gravity acting like cosmic traffic cops. As ring particles drift inward or outward, the gentle but persistent tug from these moons herds them back into line, confining the dark material into those stark, narrow corridors. Humanity almost missed them entirely. They were not discovered by direct observation, but by accident. In 1977, astronomers were using a high-altitude telescope to watch the star SAO 158687 as Uranus passed in front of it, a technique called a stellar occultation. They expected the star to simply wink out behind the planet. Instead, it flickered several times both before and after the main event. Something was blocking the starlight, something orbiting Uranus. The rings had announced themselves not by shining, but by stealing starlight. When Voyager 2 raced past in 1986, it captured their dim profiles against the blackness of space, confirming they were as dark as soot. Later, the Hubble Space Telescope would glimpse them from Earth orbit, their faint arcs a testament to a system defined by erosion and confinement. They are not the glorious remnants of a bright, icy disk, but the dark, processed leftovers of a more violent past, perhaps the pulverized remains of one or more of those fractured moons, ground into dust and then stained by the planet's own harsh radiation. This raises a deeper question about the entire Uranian neighborhood. If the rings are the debris of destruction and the moons are a collection of broken worlds, what cataclysm could have created such a system? The answer may lie with the strangest moon of them all. Miranda's fractured surface is a testament to cosmic violence, but it is the planet itself that orchestrates the most profound seasonal drama in our solar system. Those 42-year seasons are not a gentle cycle of change. They are a slow, relentless tidal force reshaping the entire world. For over 2 decades of constant sunlight, one pole bakes under a sun that never sets, a sun so distant it is merely a bright star, yet its energy accumulates day after day, year after year without respite. The opposite hemisphere languishes in a deep freeze so absolute it makes the dark side of our moon seem hospitable. You would think such an extreme imbalance would create a planet of perpetual, raging storms, a world torn between a superheated pole and a cryogenic one. Yet when Voyager 2 flew by in 1986, it saw almost nothing. Its cameras revealed a nearly featureless blue-green sphere, a billiard ball suspended in space. The atmosphere appeared calm, bland, and utterly boring, a profound disappointment that deepened the mystery of the ice giant. How could a planet with the most extreme seasonal forcing in the solar system have no visible weather to show for it? The answer, it turns out, was one of timing and technology. Voyager 2 arrived during Uranian summer when the sun was shining directly on the South Pole. Scientists now believe the planet was in a quiescent, deeply frozen state, its atmosphere so cold and stratified that large-scale storm formation was suppressed. It was like catching a hurricane-prone ocean on the one perfectly calm day of the century. Our understanding changed completely with the Hubble Space Telescope and powerful ground-based observatories like the Keck. Starting in the 2000s, as Uranus moved towards its equinox and sunlight began to spread more evenly across its latitudes, the planet woke up. Astronomers began to observe colossal storms, bright cloud features thousands of miles across, and bands of high-altitude haze. These were not subtle changes. They were titanic outbursts of weather, massive convective eruptions that dwarfed terrestrial hurricanes. This presents the central puzzle. What is the engine for these giant storms? Jupiter and Saturn have furious internal heat to drive their weather. Neptune, though farther from the Sun, radiates immense internal energy that powers the fastest winds in the solar system. Uranus, we believed, had almost none of that internal fire. So with so little heat bubbling up from below, what force is stirring the pot? Scientists are exploring two fascinating possibilities. The first involves sunlight itself, but in a way unique to Uranus. During its decades-long summer, sunlight can penetrate deep into the atmosphere over the illuminated pole, perhaps reaching layers that are normally insulated. This slow, steady deposition of solar energy might act like a giant battery, charging the atmospheric layers with heat until it finally triggers a massive release, a planetary-scale belch of convective energy that erupts as a continent-sized storm. The second possibility is that we have simply misunderstood the interior. Perhaps Uranus does have internal heat, but it is trapped or released in sporadic, catastrophic bursts rather than a steady flow. There could be layers within its slushy mantle that occasionally overturn, like a lava lamp with an immensely slow heartbeat, sending plumes of warm material soaring upward to disrupt the atmosphere. The emerging picture is of a world with a delayed reaction, a climate with incredible inertia. It does not respond to seasonal changes in real time, but stores energy for decades before unleashing it in sudden, spectacular fits. Uranus is not bland. It is a world of profound patience, building up pressure across human lifetimes until it finally expresses itself in storms that would swallow our planet whole. This slow-motion climate forces us to ask what other surprises are hidden beneath that calm blue facade, particularly in the composition of the air itself. Beneath those continent-sized storms lies an ocean, but not of water as we know it. The blue face of Uranus is a thin, deceptive mask. Below the upper clouds of hydrogen and helium lies the true body of the ice giant, a vast and alien interior that makes up most of its mass. This is the icy mantle, a region of profound mystery where familiar substances are transformed into something utterly otherworldly. Scientists believe this mantle is a deep, slushy layer of water, ammonia, and methane ices. But here, the word ice is a dangerous misnomer. We are not talking about frozen lakes or glaciers. Under the crushing pressure of thousands of Earth atmospheres and temperatures reaching thousands of degrees, these materials enter states of matter that defy simple categories. The water, in particular, is thought to exist as superionic ice. Imagine the rigid crystal structure of an ice cube, but with the oxygen atoms locked in place while the hydrogen ions flow freely through the lattice like a liquid metal. This creates a bizarre, electrically conductive slush that is both solid and fluid at the same time. a form of matter that can only exist in the heart of a giant planet or in the most advanced laboratories on Earth for mere fractions of a second. The ammonia and methane mix into this exotic soup, further complicating its properties and behavior. The great uncertainty is the structure of this mantle. Is it a distinct, well-defined layer like the white of an egg surrounding a rocky core? Or is the transition from the gaseous outer envelope to the slushy mantle and down to the possible solid core a more gradual, fuzzy gradient, with materials blending into one another over thousands of miles? Our models are educated guesses based on gravity measurements and our understanding of physics under extreme conditions, but the truth remains hidden beneath those opaque blue clouds. This exotic mantle is not a passive layer, it is the engine for Uranus's greatest oddities. It is almost certainly the source of that lopsided, chaotic magnetic field. On Earth, our magnetic field is generated by the churning of molten iron in a rotating metallic core. Uranus lacks such a core. Instead, scientists believe that the convecting motions within that electrically conductive superionic slush act as a planetary dynamo. But because this material is not a uniform, spinning ball of metal, but a vast, uneven, and possibly layered ocean, the magnetic field it generates is skewed off-center and wildly unstable. It is a magnetic field born from a form of matter we can barely comprehend. The mantle's composition and behavior also hold the key to the planet's missing heat. Its specific arrangement might act as a near-perfect insulator, trapping the primordial warmth of formation deep within the planet and explaining why Uranus radiates so little energy into space. Alternatively, the mantle could be slowly overturning in massive, sluggish plumes, releasing heat in sporadic bursts that trigger those delayed, giant storms we observe decades later. Every strange characteristic of Uranus, from its silent cold to its drunken magnetism, ultimately traces back to the secrets buried in this deep, dark, slushy sea. And if the planet's interior is this bizarre, what does it mean for the material that might be falling through it, deep within that alien slush, under pressures that crush matter into new forms? Something even more incredible may be happening. Scientists theorize that the intense heat and pressure inside Uranus could be literally manufacturing diamonds. It begins with the methane gas that gives the planet its blue-green hue. Under the crushing weight of the atmosphere, methane molecules are squeezed until their carbon and hydrogen atoms are torn apart. The carbon atoms, freed from their bonds, are then subjected to forces so immense they begin to link together, crystallizing into the hardest substance known. These microscopic diamond seeds would then begin to fall. Picture this not as gentle snow, but as a relentless, hypervelocity hail. Gravity pulls these carbon crystals deeper into the planet through the strange slush of the mantle. As they descend, they grow, aggregating into stones, perhaps even into mountains of gemstone. The journey ends thousands of miles down, where they are thought to collect in a thick layer around the planet's core, a glittering, frozen crust of unimaginable wealth. This is not science fiction. It is a serious hypothesis supported by laboratory experiments where scientists use powerful lasers to recreate the conditions inside ice giants, successfully producing tiny nanodiamonds from plastic. The process suggests that within Uranus and likely Neptune, it may be raining diamonds right now, a continuous, slow-motion glitter storm hidden beneath the clouds. But if the planet's interior is forging precious stones, its gravitational influence is sculpting worlds of pure chaos in the space around it. A glittering diamond rain falls toward a silent core, while far above, another world bears the scars of a very different kind of inner fire. Among Uranus's broken family, Ariel stands out as an enigma of youth. It is the brightest and possibly the geologically youngest of the major moons, its surface a contradictory tapestry of smooth, repaved plains and a sprawling network of deep, meandering canyons. These are not impact craters from ancient bombardments, but tectonic wounds, evidence of a world that was once alive with internal heat. The valleys, some hundreds of miles long and over 6 miles deep, slice across the landscape like colossal claw marks. They suggest a time when Ariel's icy crust stretched and fractured on a global scale, perhaps as a warmer, slushy interior expanded. The smooth plains between these chasms look like frozen seas, areas where the old, cratered terrain was completely erased by a flood of new material. This presents the central puzzle. What force could have powered such dramatic geological activity on a moon only 700 miles across, a frozen orb so far from the sun's warmth? The answer likely involves a hidden, subterranean ocean and the ghost of a gravitational dance. The most compelling theory points to tidal heating, the same process that keeps the interior of Jupiter's moon Io molten. In the past, Ariel's orbit may have been locked in a gravitational resonance with other moons, a rhythmic tug of war with Umbriel or Miranda. As they passed each other, their mutual gravitational pulls would have flexed Ariel's interior, generating immense friction and heat. This heat could have maintained a layer of liquid water or slushy ice beneath the crust for 1 billion years, providing the energy for global tectonics and cryovolcanism. Imagine not molten rock, but water lava. Ammonia-rich water, acting as a powerful antifreeze, could have erupted from fissures, flooding the lowlands and resurfacing vast regions with smooth, fresh ice before freezing solid. This period of geological activity may have been intense but brief. The orbital resonances that powered it are unstable. Over time, the delicate gravitational balance would have shifted, the moons drifting out of their resonant lock. Once that happened, the main source of Ariel's internal heat would have shut off. The subsurface ocean would have frozen, the cryovolcanoes would have fallen silent, and the moon would have entered the deep freeze we see today, preserving its youthful face as a snapshot of its final fiery chapter. Ariel's grooved terrain finds eerie echoes across the solar system, from the global cracks on Jupiter's Europa to the similar fault valleys on Saturn's Enceladus. Each is a testament to the power of tidal forces to breathe geological life into frozen worlds. Yet Ariel's activity has ceased, leaving it as a frozen fossil of that process, while Europa and Enceladus remain active today. This comparison raises a haunting question for Uranus's entire moon system. Were they all once part of a grand, resonant chorus that fell silent, leaving some worlds like Ariel freshly paved and others like Miranda brutally shattered? The silence that followed may have allowed something else to take shape in the darkness above the poles. Ariel's youthful face has a stark and ancient twin. Umbriel is the shadow among Uranus's major moons, a world cloaked in profound darkness. Its surface is one of the darkest in the entire solar system, reflecting only about half as much light as a lump of charcoal. This is not a world of recent geological activity or fresh ice, but a frozen museum of cosmic violence. Every inch of Umbriel is ancient, pockmarked by countless craters that tell a story of relentless bombardment over billions of years, with no internal heat to erase the scars. The central mystery is not what happened to Umbriel, but what it is made of. What process could have painted this entire 700-mile wide world in such a uniform coat of pitch-black material? Scientists see two compelling possibilities, each pointing to a different history of the Uranian system. The first is that Umbriel is simply primordial. It may have formed from the original, dark debris that coalesced around Uranus, a dirty snowball that never had the chance to be cleaned or resurfaced. Its composition could be rich in dark, organic compounds and carbon, a fossil from the solar system's earliest, most chemically primitive days. The second, more dramatic theory involves a celestial paint job. In the chaotic early system, when impacts were frequent and violent, one of the other moons, perhaps one even darker than Umbriel, could have been struck a catastrophic blow. The resulting debris cloud, filled with fine, dark dust, might have slowly spiraled inward, settling over Umbriel like a blanket of soot. Because Umbriel lacks any geological activity to bury or refresh its surface, that dark coating simply stayed put, preserved for eons. This theory of intermoon pollution adds a layer of interconnected violence to the Uranian family, where the destruction of one world permanently stained another. Yet even on this world of shadows, there is a single, brilliant anomaly. Near Umbriel's equator lies Wonder Crater, a wide impact basin with a perfectly circular, bright ring of material on its floor. It looks like a white target painted on a black canvas. This bright material is almost certainly water ice, excavated from beneath the dark surface layer by the impact that created Wonder. The puzzle is why this ice remains so conspicuously bright. On other dark moons, exposed ice would gradually be darkened by the relentless rain of radiation and micrometeorites, a process called space weathering. The persistence of Wonder's bright ring suggests that either the impact was relatively recent in geological terms, or that some process is actively keeping the ice clean. Perhaps tiny landslides on the crater's walls continually expose fresh, bright ice from below the dark veneer. Umbriel, therefore, presents a double mystery: the origin of its global darkness and the reason for its one defiant spot of light. It is a silent, cratered archive, holding clues to the system's violent beginnings and the slow, relentless processes that color worlds in the eternal night of the outer solar system. Umbriel's silent darkness gives way to a world of titanic scars. Teutonia, the largest moon of Uranus, is a landscape defined by rupture. Across its 1,000-mile-wide face runs a colossal wound known as Messina Chasmata, a canyon system so vast it makes Earth's Grand Canyon look like a scratch. This is not a single valley but a network of gigantic fractures, some over 900 miles long and plunging miles deep, a web of cracks that seems to encircle the entire globe. These are not the results of external bombardment but of internal stress, the unmistakable signature of a world that literally burst open from within. The leading explanation is as simple as it is dramatic. Teutonia once had a heart of liquid water and it froze. In its distant past, the moon may have been warm enough to maintain a subsurface ocean, kept liquid by a mix of internal radioactive heat and perhaps the gentle tug of tidal forces. But as that heat faded over billions of years, the ocean began to solidify. Water, uniquely, expands when it freezes. The growing ice within Teutonia would have exerted immense outward pressure, straining the moon's icy crust until it could no longer hold. The surface fractured on a planetary scale, splitting apart to create those monstrous canyons as the world expanded like an overfilled bottle left in a freezer. This process of global expansion suggests Teutonia was once a much more dynamic, potentially habitable world. The existence of a past ocean raises a profound and tantalizing question. Could any of that liquid remain today? Could there still be a remnant ocean, a layer of slushy, salty water trapped between the frozen outer shell and the moon's rocky core? For a world so distant and cold, it seems a remote possibility, yet the physics allows it. Ammonia or salts dissolved in the water would act as a powerful antifreeze, dramatically lowering its freezing point. The slow, decaying heat from radioactive elements in Teutonia's core could provide just enough warmth to maintain a briny, subsurface sea, even now. This same reasoning applies to its sibling, Oberon, Uranus's second-largest moon. Though more heavily cratered and seemingly less active, it too shows hints of past internal resurfacing and could harbor similar secrets deep below. If true, these moons would join an exclusive club of ocean worlds in our solar system, like Jupiter's Europa and Saturn's Enceladus. Yet the environments within Teutonia or Oberon would be profoundly more extreme, darker and colder, with any potential chemistry for life operating at an almost unimaginably slow pace. They are not promising abodes, but they are possible ones, reminding us that the conditions for liquid water, that fundamental ingredient may persist in the most unexpected and forbidding corners of our cosmic neighborhood, locked inside fractured worlds orbiting a sideways giant. Oberon holds its darkness close, like a secret buried in its oldest wounds. While Umbriel is uniformly dark, Oberon presents a more targeted mystery. Its surface is a stark patchwork of bright, icy plains and deep, shadowy craters. But within many of those craters, especially on the Moon's leading hemisphere, the side that faces forward as it orbits, the floors are coated in an enigmatic, dark red material. It looks as if someone carefully painted the bottoms of these ancient impact sites with a layer of cosmic soot. This is not a global stain, but a selective one, and that selectivity is the key to unraveling its origin. Two compelling theories compete to explain these strange deposits, each pointing to a different chapter in Oberon's violent history. The first theory imagines a moon that was once geologically alive. In the distant past, Oberon may have experienced cryovolcanism, but instead of erupting clean water or ammonia, its subsurface ocean or slushy mantle could have been laced with complex, carbon-rich organic compounds. When this dark, briny magma erupted onto the surface, perhaps triggered by a large impact, it would have flowed like a thick, tarry sludge before freezing solid, preferentially filling the low-lying crater floors. Over eons, the brighter, cleaner ice around it would have been gardened by micrometeorites, but the dark material in the protected crater basins remained, a frozen record of a single, dirty eruption. The second theory requires no internal activity at all. It suggests the dark material was always there, lying in a layer beneath a brighter, icy crust. When asteroids struck Oberon, they punched through that bright veneer, excavating and melting the dark, carbonaceous material from below. The impact melt and debris would then have settled back down, concentrating in the crater bowls as a permanent dark stain. This would make Oberon's craters natural drill holes, revealing the Moon's hidden primordial composition. The Moon's heavily cratered, ancient surface supports this idea. Oberon looks like a fossil, a world that has seen little geological change for billions of years. Its craters are not erased by tectonic forces or icy lava flows. They accumulate one on top of another, preserving a record of the final, violent stages of planetary formation. This makes Oberon more than just another moon. It is a time capsule. The dark material in its craters could be pristine stuff from the very edge of the early solar system, organic compounds that have been locked in deep freeze since the dawn of our planetary system. Studying it is like analyzing the ingredients that were available when Uranus and its family first coalesced from the cosmic cloud. Yet, if Oberon is such a pristine relic, its very existence poses a new puzzle for the entire system. Oberon's ancient craters may hold primordial secrets, but they are not the only wanderers in this system. Far beyond the orbits of these major moons, in the deep, cold reaches of Uranus's gravitational influence, a different class of object circles the planet. These are the irregular moons, a collection of at least 9 small, dark worlds moving in distant, tilted, and often backwards orbits. They are cosmic strays, and their very presence poses a profound capture puzzle. The challenge is one of celestial mechanics. For a giant planet like Uranus to capture a free-flying object from the depths of the solar system, the event must be exquisitely precise. An asteroid or comet approaching from the Kuiper belt would typically have too much speed, too much orbital energy, to simply fall into orbit around the planet. It would swing by in a hyperbolic curve like a spacecraft on a flyby and continue on its way, never to return. To be captured, that object must lose a significant amount of its energy, and it must do so in a single, fleeting encounter. How is that possible? The leading theory involves a third body and a cosmic game of gravitational billiards. In the chaotic early solar system, these small worlds may not have been alone. They could have been part of a binary pair, 2 objects orbiting each other as they traveled through space. If such a binary passed too close to Uranus, the planet's immense gravity could have torn the pair apart. One member might be flung away at high speed, carrying away the excess orbital energy, while the other, now robbed of its momentum, is left behind, trapped in a wide, looping orbit around the planet. It is a delicate and violent process, but one that fits the mathematical models. Yet, this elegant solution raises another question. Could so many irregular moons all have been captured this way, one by one? An alternative theory suggests a more orderly, if still ancient, origin. Uranus may have possessed a much more extensive and long-lived disk of dust and gas in its youth than we currently assume. Within this extended disk, small objects could have formed in place or more easily been slowed down and captured through friction with the primordial gas. Their dark, red surfaces provide a crucial clue. Spectral analysis shows they are coated in complex organic compounds, similar to the darkest objects in the Kuiper belt and the nuclei of comets. This strongly suggests they are not native to the Uranian system, but captured visitors from the solar system's frozen frontier. They are likely primitive, carbon-rich bodies that have been orbiting backwards and at severe angles for billions of years, preserved in the deep freeze of the outer system. Their existence paints a picture of a young Uranus as a gravitational net, snagging passing relics from the dawn of planetary formation and binding them into its own strange family, a collection of cosmic souvenirs from a time when the giant planets themselves were still on the move. These captured strays orbit in the distant dark, but closer to the planet within the rings themselves. Another class of unseen moon performs a delicate gravitational ballet. The stark, narrow rings of Uranus are not static decorations, they are dynamic structures, and their very existence points to hidden architects. The epsilon ring, a perfect cosmic thread, maintains its razor-thin width against all odds. Left to their own devices, the countless particles within a ring would naturally spread out over time, their orbits perturbed by the gravity of larger moons and by collisions with one another. The fact that Uranus's rings remain so sharply defined means something is actively herding them, confining this dark material into precise lanes. That something is almost certainly a population of tiny shepherd moons embedded within or just beside the rings themselves. The principle is elegant. Imagine two small moons, one orbiting just inside a ring and one just outside. As ring particles drift inward, they approach the inner shepherd moon. Its gravity gives them a slight tug, a boost of energy that pushes them back outward into the ring. Conversely, particles drifting outward feel a gentle pull from the outer shepherd moon, slowing them down and nudging them back inward. It is a continuous, gentle process, a gravitational feedback loop that acts like bumpers on a cosmic bowling lane, keeping the ring particles neatly in their place. Voyager 2's brief flyby provided tantalizing hints that these moonlets are real. Its images of the epsilon ring showed slight kinks and waves along its edges, distortions consistent with the gravitational influence of small, unseen bodies orbiting nearby. Yet the spacecraft's cameras were not powerful enough to definitively spot these elusive shepherds, leaving their existence in the realm of strong inference rather than confirmed fact. This presents a practical mystery. If shepherd moons are sculpting the rings, why have we not found more of them? The answer lies in their nature and our limited view. These moonlets are likely very small, perhaps only a few miles across, and composed of the same incredibly dark material as the rings themselves. They are essentially lumps of that ring material, just massive enough to exert a gravitational influence but too small and non-reflective to be easily seen from Earth or by a passing probe. Spotting them is like trying to find a piece of charcoal floating in front of a black velvet curtain under the dim light of a distant star. Their orbits may also be chaotic or unstable, shifting over time as they interact with the ring particles and each other, making them moving targets for our telescopes. Future missions hold the key to finding these gravitational puppeteers. A dedicated Uranus orbiter, equipped with modern, high-resolution cameras and sensitive detectors, could stare at the rings for years. By meticulously tracking the motions of individual ring particles and mapping the subtle ripples and waves that propagate through the rings, scientists could pinpoint the exact locations and masses of the shepherd moons, even if they remain too dark to see directly. It would be a detective story written in gravity, revealing the hidden hands that shape these dark bands. Confirming their existence would do more than solve a puzzle. It would provide a masterclass in celestial mechanics, showing us how even the faintest whispers of gravity can impose exquisite order on the chaos of space. And if such small moons can wield such precise control, what does that suggest about the forces that once governed the formation of the entire fractured Uranian family? The hidden shepherds sculpting the rings work in a realm of exquisite precision, but high above them, in the planet's atmosphere, chaos erupts on a scale that dwarfs continents. Uranus has its own version of the monster storms seen on Jupiter and Neptune, but with a deeply Uranian twist. They are ghosts. These are the dark spots of Uranus, transient, swirling vortexes the size of North America that appear without warning and vanish just as mysteriously. The first definitive glimpse came from the Hubble Space Telescope in 2006. Where Voyager had seen only a placid blue ball 2 decades prior, Hubble's keen eye detected a brooding, dark oval in the northern hemisphere, a giant atmospheric storm raging in the frozen hydrogen and helium. It was a shock. Here was proof that Uranus, for all its apparent calm, could muster weather as violent as any in the solar system. Yet when astronomers looked again in subsequent years, the spot was gone, faded back into the featureless blue. Subsequent Hubble observations have caught other dark spots appearing and disappearing, each one a fleeting phantom in the planet's upper cloud decks. These spots are not clouds in the traditional sense, but holes. They are colossal anticyclonic storms, vast high-pressure vortexes where atmospheric gases are sinking rather than rising. As material descends in the center of the vortex, it clears away the upper, brighter haze of methane ice crystals, opening a window to a deeper, darker layer of the atmosphere. From our perspective, this creates a distinct dark blotch against the brighter blue background, a swirling eye staring out from the depths. On Neptune, its famous Great Dark Spot persisted for years, a semi-permanent fixture powered by the planet's fierce internal heat. The dark spots of Uranus, by stark contrast, seem to be short-lived phenomena, often lasting only months or a few years before dissipating. This ephemeral nature is the core of the mystery. What creates these giant storms so quickly, and why do they lack the staying power of their Neptunian cousins? The answer circles back to the fundamental Uranian paradox, the missing heat. Neptune's raging storms are stoked by a tremendous internal furnace, providing a constant, energetic churn from below that can sustain massive vortexes for long periods. Uranus, with its eerily quiet interior, lacks that steady power source. Instead, scientists believe its giant storms are likely solar-powered, but in a delayed and inefficient way. As sunlight finally reaches the planet's equator and mid-latitudes during its long march toward equinox, it may trigger instability in the atmosphere's layered structure. This solar energy might be enough to spawn a colossal convective plume or sheer instability that organizes itself into a dark vortex. But without a strong, continuous heat flow from the planet's interior to keep driving it, the storm quickly runs out of energy, choked by the surrounding atmospheric dynamics and fading back into the background. It is like trying to keep a campfire blazing with only occasional puffs of air instead of a steady supply of wood. Comparing Hubble images from different years tells a story of a capricious and changing world. One frame shows a serene, uniform disk. Another, taken just a year later, reveals a stark, dark blemish. A third, a few years after that, shows the blemish gone, replaced perhaps by a bright cloud cap at the pole. This variability forces a profound reassessment. Uranus is not a dead world climatically, but a world with a weak and intermittent heartbeat. Its atmosphere seems to operate in fits and starts, building up energy slowly, perhaps over decades of seasonal heating, and then releasing it in these sudden, violent outbursts that vanish almost as quickly as they came. The dark spots are the most visible symptoms of this erratic climate, the planet's way of venting built-up pressure in spectacular but unsustainable bursts. Their fleeting brilliance raises a deeper question about what other, subtler forms of weather churn beneath the visible cloud tops, unseen by our telescopes, in the deep, cold heart of this sideways world. These ghostly storms rage in an atmosphere that itself is slowly, invisibly bleeding away into space. High above the cloud tops where the dark spots swirl, the thin air of Uranus stretches into a vast, diffuse shroud called the hydrogen corona. This is not a fiery crown like the Sun's, but a tenuous cloud of individual hydrogen atoms, the lightest element, escaping the weak grip of the planet's gravity and forming a giant, invisible halo. All the giant planets have such coronas, but Uranus presents a specific and puzzling mismatch. When Voyager 2 sped through this region in 1986, its instruments took a direct snapshot of the corona's conditions. Decades later, powerful telescopes on Earth and in space, like the Hubble, tried to measure the same thing from a distance using ultraviolet light. The two sets of data tell subtly different stories. They disagree on the precise density of this escaping hydrogen haze and, more importantly, on its temperature. Is it a relatively warm, puffy envelope or a colder, more compact one? This is not just a minor calibration error. It is a clue that something dynamic and poorly understood is happening in the planet's upper atmospheric engine. The temperature and density of the corona are controlled by a complex tug of war. Energy from the distant sun, in the form of extreme ultraviolet light, hits the upper atmosphere and breaks apart molecules, providing the heat and the individual atoms that form the corona. The planet's own magnetic field, with its wild wobble, then channels and accelerates charged particles, adding more energy. Meanwhile, the solar wind, a constant stream of charged particles from the sun, presses against this extended atmosphere, potentially stripping it away and shaping its outer boundary. The discrepancy between the Voyager in situ measurements and the remote observations suggests our models of this tug of war are incomplete. Perhaps the corona changes dramatically with Uranus's extreme seasons, becoming denser or hotter when one pole is in constant sunlight. Maybe the lopsided magnetic field creates an uneven escape, with hydrogen bleeding away faster in some regions than others, a leak that isn't uniform. There could be unknown chemical processes higher up, creating a layer of haze or ions that affects how ultraviolet light passes through and is measured from Earth. Pinpointing the truth is critical because this faint, escaping haze represents the planet losing mass over geological time. Uranus will not evaporate away anytime soon, but the rate of this atmospheric loss is a key factor in its long-term evolution. Did it start with a much thicker envelope of hydrogen and helium that has been slowly scoured away over billions of years? Is it losing its primordial atmosphere faster than its twin, Neptune? Answering the corona discrepancy is like finding the correct setting for a slow-motion leak. By understanding the processes at work today, scientists can run the clock backward to model the planet's ancient atmosphere and forward to predict its distant future. It turns the entire planet into a laboratory for atmospheric escape, a process that shaped the destinies of worlds like Mars and may be happening right now on exoplanets orbiting distant stars. The silent whisper of escaping hydrogen holds the history of the ice giant's air, written in a code we are still learning to read. That faint whisper of escaping hydrogen is not the only sound from this silent giant. Uranus sings, but its song is a broken, crackling melody unlike any other in our solar system. When Voyager 2 raced past in 1986, its plasma wave instrument picked up something extraordinary, strange radio bursts crackling from the planet's magnetic environment. These were not the smooth, predictable radio waves generated by Jupiter or Saturn, but sharp, sporadic, and highly structured pulses, a form of planetary static with a unique Uranian signature. The source of this cosmic radio noise is a direct consequence of the planet's greatest deformity, its lopsided and tilted magnetic field. On a planet with a symmetrical field, charged particles like electrons spiral in orderly paths along the magnetic lines, emitting radio waves at a frequency tied to the strength of the field. It is a predictable process, a steady hum, but Uranus offers no such order. Its magnetic field is a tangled, wobbling mess, and as it corkscrews through space with the planet's rotation, it whips these charged particles into a frenzy. The particles do not follow clean, looping paths. They are accelerated and scattered chaotically along the skewed and off-center field lines. This violent, disorganized motion generates those sharp, bursty radio emissions, the sound of a magnetic field in severe distress. Think of it like the difference between a smoothly bowed violin string and the chaotic snap of a breaking cable. One produces a clear note, the other a jarring, unpredictable crackle. Uranus's radio voice is the sound of that cable snapping over and over again, timed to the planet's 17-hour rotation. This peculiar radio signature is more than just a curiosity, it is a remote diagnostic tool. Just as a doctor listens to your heartbeat, planetary scientists can listen to these radio bursts to infer the health and dynamics of a world's hidden interior. The frequency and intensity of the emissions are tied directly to the strength and configuration of the magnetic field deep within the planet. By monitoring these radio crackles from Earth using powerful radio telescopes, astronomers could, in theory, detect changes in Uranus's magnetosphere over time. If the planet's internal dynamo, that churning ocean of supersonic slush, were to undergo a shift or an upheaval, it would alter the magnetic field it generates. That alteration would then change the behavior of the charged particles and ultimately the pattern of radio waves we detect. It is a long-distance probe into the heart of the ice giant. A sustained campaign of radio observations could reveal whether Uranus's magnetic field is stable or if it undergoes strange cycles or reversals, much like Earth's field flips polarity every few 100,000 years. Given the field's current chaotic state, any change could be dramatic. Monitoring this broken song from across 2 billion miles of space offers our best chance to understand the real-time, or rather decade-time, dynamics of an alien world's deep interior, all without ever sending another probe. It turns the planet's greatest deformity into a cosmic broadcast, a signal of the profound and ongoing turmoil hidden beneath that calm blue face. That broken radio song is a direct broadcast from a magnetic field in chaos, a field that is fundamentally lopsided. This profound asymmetry forces us to circle back to the original, defining mystery of Uranus because it is all connected. The planet's extreme tilt, its missing heat, and its drunken magnetism all seem to trace back to a single ancient catastrophe. Yet one observation stands as a monumental challenge to that clean story, a puzzle written in the paths of its moons. Every single one of Uranus's major moons orbits in perfect alignment with the planet's equator. They form a neat, flat disk like a miniature solar system, all spinning around the planet's waist as it rolls on its side around the Sun. This perfect orbital alignment is the killer detail for the simple giant impact theory. Think of the solar system as a spinning top. If you give that top a sharp, sideways smack, the top itself will tilt, but the dust motes floating around it will not automatically follow. They will keep orbiting in their original plane, now slicing across the new, tilted equator of the top. For Uranus, if a colossal impact knocked the fully formed planet sideways long after its moons had coalesced, we would expect to see those moons orbiting in the old, upright plane of the original solar system. The fact that they do not, that the entire family is tilted in unison, presents astronomers with a stark choice. Either the cataclysm happened so early that it reshaped the entire system from the ground up, or our understanding of the impact itself needs a radical revision. The first possibility is that the impact occurred when Uranus was still a young protoplanet, surrounded by a vast, swirling disk of gas and dust, the material from which its moons would eventually form. A titanic collision at this stage would not just knock the planet over, it would violently disrupt that primordial disk. The debris would be sent into a chaotic tumble, but over time, gravity and friction would cause it to settle into a new, flat disk aligned with the planet's freshly tilted equator. The moons then formed from this new, realigned disk, locking them into their current orbits from birth. In this scenario, the moons we see today are not survivors of the impact, but its children born from the wreckage. The second possibility is far stranger and demands a collision of almost impossible precision. What if the impacting body was not a single massive projectile, but something more like a massive, diffuse swarm of planetesimals or a series of smaller impacts? Or what if the impact was so perfectly aimed and so gargantuan that it did not just hit the planet, but delivered an angular momentum shock so profound that it tilted the entire system, a planet, disk, and all in one coherent motion? Visualizing this requires a shift from thinking in 2 dimensions to 3. Picture Uranus not as a simple ball, but as the central mass within a vast, invisible sphere of influence, its gravity holding a flat, pancake-like disk of material. A giant impact from the side would send a shockwave through this entire structure. If the impactor was massive enough and the disk tenuous enough, the gravitational coupling between the planet and its surrounding material could be strong enough to drag the entire disk along with the planet's new tilt, like tipping a plate of water and having all the water slide as one unit. This is an elegant solution, but it requires a very specific set of initial conditions, a cosmic billiard shot of unbelievable luck and force. The aligned orbits of the moons are not just a curious fact, they are a forensic clue at the scene of a 4.5 billion-year-old crime. They tell us that whatever happened to Uranus did not happen to Uranus alone. It was a systemic event, a trauma that reshaped the destiny of an entire miniature planetary system, leaving behind a family of worlds forever circling their sideways parent in silent, perfect unison. That perfect, tilted family orbits a world of one specific and puzzling color. Uranus is not just blue, it is a particular shade of pale cyan, a washed-out aquamarine that stands in stark contrast to the deep, vibrant azure of its twin Neptune. Both planets are ice giants, both have atmospheres rich in methane, so why the difference in hue? The answer begins with a simple fact of light, but quickly descends into a mystery of atmospheric chemistry. Sunlight, which appears white, contains all the colors of the rainbow. When that light hits the upper atmosphere of Uranus, methane gas acts as a filter. It is exceptionally good at absorbing the longer wavelengths of light, the reds and oranges. What gets reflected back to our eyes are the shorter wavelengths, the blues and greens. This is the foundational reason for the blue appearance of both Uranus and Neptune. But if methane alone were responsible, the 2 planets should look nearly identical. They do not. Neptune is a richer, more saturated cobalt blue, while Uranus is a lighter, milky cyan. The key to this discrepancy likely floats high above the main cloud decks in a layer of haze. Planetary scientists believe Uranus is shrouded in a thicker, more pervasive layer of high-altitude haze than Neptune. This haze is thought to be composed of tiny particles, perhaps frozen methane ice crystals or more complex hydrocarbons created when sunlight breaks apart methane molecules. This misty veil acts like a thin coat of white paint over a blue wall. It scatters and reflects additional white light back into space, mixing with the underlying blue from the methane layer below and washing out the color, giving Uranus its distinctive pastel tone. Neptune, with a thinner or less dense haze layer, lets the deeper, pure blue of its methane atmosphere dominate. This raises an immediate question: what controls the thickness of this haze? Is it a matter of atmospheric temperature, circulation, or chemistry? The colder upper atmosphere of Uranus might be more conducive to forming and sustaining this icy haze. Alternatively, the planet's extreme seasons and lack of strong internal heat could lead to a more stagnant atmospheric structure, allowing haze particles to accumulate and linger for longer periods without being stirred down into the warmer, deeper layers where they would evaporate. The most intriguing possibility is that the haze itself is made of something we have not yet identified. Photochemistry, driven by the sun's ultraviolet light, can create a zoo of complex organic molecules in an atmosphere rich in methane. On Saturn's moon Titan, this process creates a thick, orange smog. On Uranus, it might be generating a thinner, whiter mist of exotic hydrocarbons. The precise recipe for this haze, the size and composition of its particles, remains unknown. It is a ghostly shroud that not only softens the planet's color, but may also hold clues to the complex and slow-motion chemical reactions occurring in its frozen upper air. The uniform, featureless nature of this aqua blanket is another clue. Unlike Jupiter or even Neptune, Uranus rarely shows strong cloud bands or spots that contrast with its base color, especially in its quiescent phases. This suggests the haze layer is remarkably uniform and global, smoothing over any turbulent features beneath it like a cosmic fog. The pale blue marble we see is therefore a composite portrait, a blend of simple physics and complex, hidden chemistry. It is the signature of a cold, calm, and chemically patient world, wearing its atmosphere like a perfectly smooth, yet mysteriously whitened coat of cyan paint. That pale cyan veil hides a world of atmospheric motion that defies simple logic. Uranus possesses some of the strangest wind patterns ever measured. The planet itself rotates slowly, completing a full turn in about 17 hours, but the winds within its atmosphere race at astonishing velocities, exceeding 500 miles per hour. Yet this raw speed is not the true mystery. It is the bizarre and counterintuitive profile these winds create as you move from the equator to the poles. On Earth and other giants, we expect the fastest winds to be channeled into jet streams near the equator, driven by the planet's rapid rotation. Uranus flips this expectation completely. Here, the equatorial region is a zone of relative calm, with winds that are slow, stagnant, or even blow backwards, retrograde against the planet's rotation. The real fury is confined to the middle latitudes, where those supersonic winds scream in the same direction as the planet spins. It is as if the planet's atmospheric engine is strongest not at its waist but wrapped around its shoulders, a pattern unseen anywhere else. Explaining this demands a radical rethinking of what drives weather on an ice giant. Scientists believe the answer lies in the profound shallowness of the weather layer itself. On Jupiter and Saturn, the spectacular cloud bands and storms are manifestations of deep planet-wide convection, churning from thousands of miles down. Uranus, with its missing internal heat, likely has a much thinner active layer. The dramatic weather we see may be confined to only the very top of the atmosphere, a skin-deep phenomenon perhaps just a couple hundred miles thick. Below that, the atmosphere is thought to be incredibly sluggish and uniform, a deep, still ocean of gas that does not participate in the violent motions above. This creates a profound disconnect. The winds we observe are not coupled to a deep planetary engine. Instead, they might be powered almost entirely by the faint and uneven trickle of sunlight, combined with the meager heat that does manage to seep up from the depths. The momentum for those mid-latitude jets must therefore be generated and confined within that shallow layer. One compelling model suggests that the extreme seasons play a crucial role. During the decades-long summer, one pole bakes in constant sunlight, creating a massive, slow-moving high-pressure system. The atmospheric flow from this warm pole to the dark, cold pole, deflected by the planet's rotation, could set up and reinforce those ferocious mid-latitude jets while leaving the equator as a stagnant zone in between. The retrograde winds at the equator might even be a kind of atmospheric backlash, a compensating flow as air is sucked toward the stormy middle latitudes. This shallow weather model has a startling implication. It suggests that the churning, slushy interior of Uranus, with its superionic oceans and possible diamond rain, is almost completely divorced from the blue face it shows the universe. The planet's deep heart beats in near-total silence, while its skin twitches and convulses under the distant, feeble sun. The winds are not a window into the interior, but a mask over it, a frenetic dance on the surface of a profoundly still and alien sea. This shallow, frenetic weather dances atop an abyss with no floor. One of the most fundamental mysteries of Uranus is not something it has, but something it lacks, a clear and solid surface. For a terrestrial world like Earth, the surface is obvious, the ground beneath our feet. But for an ice giant, the very idea of a surface dissolves into a profound ambiguity. Where does the planet truly begin and end? Scientists use a practical but arbitrary definition, the 1 bar pressure level. This is the altitude where the atmospheric pressure equals the air pressure at sea level on Earth. It is a convenient reference point, a place to hang our measurements, but it is no more the surface of Uranus than the top of a thundercloud is the surface of Earth. It is merely the level at which the overlying atmosphere becomes opaque to our eyes. Below this imaginary line, the descent into the true Uranus begins, a journey into states of matter that erase all familiar boundaries. The hydrogen and helium gas does not abruptly stop. Instead, it thickens gradually, like diving deeper and deeper into an ocean. With increasing pressure and temperature, these gases undergo a seamless transition into a supercritical fluid. This is a phase of matter that is neither a true liquid nor a gas, but possesses properties of both. It can flow like a fluid and diffuse through solids like a gas, a strange hot soup that fills the depths. Further down, the real transformation occurs. The water, methane, and ammonia, which we think of as gases or ices, become so compressed and heated that they form that exotic slushy mantle of superionic ices, a realm where chemistry itself is bent to extremes. The point is, there is no sharp boundary, no continental shelf, no ocean floor. The transition is a gradual gradient over thousands of miles, a slow thickening from tenuous gas to dense fluid to electrically conductive slush. This fundamental ambiguity creates ripples of uncertainty through all our models of the planet. How do we define its rotation period? We cannot time the spin of a solid core we cannot see. The 17-hour day we quote is based on the wobble of its magnetic field and the movement of cloud features in that shallow weather layer, a measurement of its outer skin, not its heart. The deep interior could, in theory, be rotating at a slightly different speed, a concept that challenges our basic understanding of a planet as a single, coherent object. This blurry interior also complicates how we map its gravity field, which is our primary tool for inferring its internal structure. On a planet with distinct layers, gravity data can reveal clear boundaries. On Uranus, the signals are smoothed and muddied by the gradual transitions, making it incredibly difficult to pinpoint where one layer ends and another begins. Is there a distinct rocky core, or is it a diffuse gradient of heavier elements mixing into the icy slush? Our simulations must make educated guesses about these fuzzy boundaries, and different assumptions lead to wildly different portraits of the planet's deep heart. The lack of a solid surface is more than a technicality, it is a philosophical challenge. It forces us to abandon terrestrial intuition and accept that a planet can be a continuum, a giant sphere of matter that simply gets denser and stranger until perhaps all definitions fail. Uranus is not a world with a surface you could stand on, but an ocean of exotic fluids you would sink through forever, a reality that makes its very nature as elusive as the boundary we try to impose upon it. This profound ambiguity about a solid surface only deepens the intrigue of what might be falling through that endless descent. One of the most captivating ideas in planetary science suggests that deep within Uranus, it is literally raining diamonds. The hypothesis begins with a simple ingredient, methane, the gas that gives the planet its blue tint. Under the crushing pressures thousands of miles down, the bonds holding methane's carbon and hydrogen atoms together are shattered. The freed carbon atoms, subjected to unimaginable force and heat, are then squeezed into the crystalline structure of diamond. These microscopic gemstones, heavier than the surrounding slushy material, would begin to sink. Picture this not as a gentle glitter, but as a hypervelocity hail. Gravity pulls these carbon crystals ever deeper, and as they fall through the exotic mantle, they could grow, aggregating into stones or even boulders of pure diamond, a relentless, glittering precipitation in the heart of the ice giant. This is not mere science fiction, it is grounded in serious laboratory work. Scientists have used powerful lasers to recreate the extreme conditions inside planets like Uranus and Neptune, compressing polystyrene, which is rich in carbon and hydrogen, in a fraction of a second. The result, the formation of tiny nanodiamonds, observed scattering like cosmic dust in the aftermath of the experiment. This provides tangible proof that the chemistry of diamond formation is not only possible but likely under such alien pressures. The debate now is not about if it happens, but about the spectacular scale and final destination of this gemstone shower. Could these diamonds grow to monumental sizes during their long fall? Some models suggest they might, creating diamond icebergs drifting in the slush. And where does the journey end? Scientists theorize that thousands of miles down above the hypothesized rocky core, there could be a thick accumulation, a layer of solid diamond, or even a strange, hot diamond ocean where carbon behaves in ways we can barely model. It is a staggering thought, an entire stratum of the planet forged from precious stone. Yet this glittering possibility also highlights a profound irony. The very process that creates this inner treasure also represents a slow leak of the planet's identity. Each diamond that forms and falls permanently sequesters carbon from the atmosphere, subtly altering the chemistry of the mantle over billions of years. This diamond rain is a beautiful, violent, and continuous transformation, a hidden alchemy that turns common gas into legendary gemstones in the eternal dark. If the planet's heart is a forge for diamonds, what other impossible chemistry is occurring in its frozen outer reaches, where the very air we breathe becomes a deadly poison? This diamond rain falls through a profound silence. Uranus possesses a magnetic field of bizarre geometry, yet the vast space it governs, its magnetosphere, is strangely hushed. Around Jupiter and Saturn, their magnetospheres roar with activity, crackling with radio waves, glowing with intense auroras, and teeming with plasma from their volcanic moons. Uranus, by contrast, whispers. Its magnetosphere is quiet, orderly, and depleted, a ghost town compared to the bustling cities around other giants. This tranquility is deeply puzzling. Given the planet's lopsided, tumbling magnetic field, you would expect a correspondingly chaotic and energetic magnetic environment, a perpetual storm of trapped particles. Instead, we find a realm of eerie calm. The primary reason appears to be a simple lack of fuel. Jupiter's magnetosphere is supercharged by Io, which blasts a ton of volcanic material into space every second, creating a dense, donut-shaped plasma torus. Saturn's is fed by the icy geysers of Enceladus. Uranus has no such internal engine. Its moons are frozen, geologically dead worlds. Without a major source of plasma from within, the magnetosphere is starved, running on the thin trickle of particles it captures from the solar wind or that sputter off the surfaces of its own quiet moons. This creates a magnetosphere that is fundamentally different in character. It is not driven from the inside out, but shaped from the outside in by the solar wind. The solar wind, that stream of charged particles from the sun, presses against the magnetic bubble and sculpts it. Because Uranus lacks a dense internal plasma to push back, its magnetosphere is more compliant, more easily compressed and stretched by the solar wind's pressure. When Voyager 2 flew through, it found a magnetosphere that was surprisingly empty and well-ordered, despite the drunken wobble of the magnetic poles at its heart. This quiet extends to the planet's radiation belts, regions where charged particles are trapped by the magnetic field, spiraling around the lines of force. At Uranus, these belts are weak and strangely structured. The tumbling of the magnetic field does not create a stable, symmetrical trapping region like Earth's Van Allen belts. Instead, the particles are subjected to a constantly changing geometry. As the off-center, tilted field corkscrews through space, the paths for these particles are scrambled. Many likely escape quickly, dumped into the polar atmosphere to create faint auroras or simply lost to space. This results in radiation belts that are both weaker and more diffuse than those of other giants, another signature of a magnetosphere running on empty. The profound quiet here is a direct consequence of the entire Uranian system's deep freeze. No volcanic fires, no subsurface oceans spewing plumes, just the slow, cold whisper of the solar wind against a magnetic field born from a slushy, alien interior. It is a silence that speaks volumes about the isolation and inactivity of this distant kingdom. A magnetic bubble so quiet you could almost hear the diamonds falling in the dark below. That profound quiet in its magnetic bubble stands in stark contrast to the slow, epic drama unfolding in its atmosphere over timescales that dwarf human history. The true climate of Uranus is not measured in years, but in millennia, a slow-motion ballet of light and dark where seasons last for generations, with one pole baking in sunlight for 21 Earth years while the other freezes in endless night. Then slowly swapping roles over the next 84-year orbit, the planet experiences climate forcing of a magnitude we can barely comprehend. This raises a grand, almost philosophical mystery. How does such a world evolve over astronomical time? Does it settle into a predictable rhythm, or does it lurch between wildly different climatic states over millions of years? Current models, built on the snapshot from Voyager and decades of telescope observations, suggest Uranus is a world of profound climatic inertia, but with a terrifying capacity for delayed fury. The key is the storage and release of solar energy. During its decades-long summer, sunlight is not just absorbed, it is banked. It penetrates the cold, deep atmosphere over the illuminated pole, warming layers of gas that retain that heat with stubborn efficiency. This energy does not immediately erupt into storms. It accumulates, like compressing a spring over an entire human lifetime. The planet's weak internal heat flow means this solar input is the dominant driver, but its effects are not felt in real time. The climate responds with a lag that could be decades long. This leads to a fascinating prediction. The most intense global storm activity may not occur at the height of summer, but as the planet approaches its equinox when sunlight begins to spread across the equator. It is then that the stored energy from the summer pole, combined with the new influx of sunlight at lower latitudes, could trigger a planetary scale upheaval. The atmosphere, after decades of slow charging, might finally release its pent-up energy in a cascade of continent-sized convective plumes, dark spots, and bright cloud eruptions that could wreathe the entire planet in turbulence for years. We may have already witnessed the prelude to this. The remarkable storms observed by Hubble and ground telescopes in the 2000s occurred as Uranus moved away from its 1986 solstice and toward the equinox it reached in 2007. That outburst of activity after the bland face shown to Voyager fits the model of a delayed climatic explosion. The coming decades offer a rare and critical test. As Uranus continues its march toward its next northern summer solstice in 2049, and then onward to another equinox around the year 2100, astronomers have a unique opportunity. By monitoring the planet continuously with the James Webb Space Telescope and next-generation observatories, we can watch this slow-motion climate engine in action. Will the northern hemisphere, now emerging from its long winter, begin to stir with faint cloud features? Will the southern hemisphere, moving into darkness, slowly calm down? Most importantly, will we see another great outburst of storms as the next equinox approaches in a century? These observations will either confirm our models of a climate built on decades of energy storage, or reveal something even stranger, perhaps a world that switches between multiple stable climate states over its multi-million-year journey around the Sun. The climate history of Uranus is written in ice and gas, in a script where each chapter is longer than all of human civilization, waiting for patient observers to read its next slowly turning page. The slow-motion climate of Uranus is a story written over eons, but its opening chapter is perhaps the most perplexing of all. The entire Uranian system, from its tilted planet to its fractured moons, presents a profound formation puzzle. It simply does not fit the standard model of how giant planets are supposed to be built. Jupiter and Saturn are gas giants, massive spheres dominated by hydrogen and helium captured directly from the primordial solar nebula. Uranus and Neptune, however, are ice giants. Their bulk is not light gas, but a dense, heavy mixture of water, ammonia, methane, and rock, wrapped in a relatively thin envelope of hydrogen and helium. This fundamental difference in recipe is the first major clue. It suggests Uranus formed under different conditions in a different neighborhood and perhaps at a different time than its larger cousins. The leading theory paints a picture of a slower, more difficult birth. In the crowded early solar system, the region where Uranus now orbits may have been too sparse or the process too slow for it to rapidly grab vast amounts of light gas before the young sun's fierce solar wind blew the nebula away. Instead, it likely began as a massive core of rock and ice, a planetary embryo 10 to 15 times the mass of Earth. This core grew by accreting countless icy planetesimals from the frigid outer disk, those primordial building blocks rich in water and frozen gases. Only after this solid foundation was substantial enough did its gravity become strong enough to attract a modest cloak of the surrounding hydrogen and helium, dressing its icy heart in a thin gaseous shroud. This explains its composition, a world that is fundamentally an icy rocky body with an atmospheric afterthought, rather than a ball of gas with a small core. But this story gets tangled when we try to explain its location. If Uranus is made of icy material, logic says it should have formed much farther from the Sun, out where those volatile ices were plentiful and stable. So why is it here? This introduces the grand and chaotic idea of planetary migration. In the dynamic early solar system, the giant planets did not form and stay put. Gravitational interactions with the vast sea of leftover planetesimals could have caused them to drift. Uranus may well have been born in the cold, distant darkness beyond Neptune, a true outer realm world. Over millions of years, a gravitational dance with Jupiter and Saturn, or the slow scattering of countless smaller objects, could have nudged it inward to its present orbit. This migration would have been a violent trek, scattering the primordial Kuiper belt and hurling comets everywhere, potentially explaining some of the bombardment history etched on its moons. Yet the planet's extreme tilt throws a wrench into even this complex narrative. A migration event alone does not easily explain a 98-degree roll. This brings us back to the cataclysm hypothesis, but with a new layer. Could the migration itself have triggered the collision? As Uranus moved through a denser region of the primordial disk, the chances of a massive impact would have increased dramatically. Or perhaps the tilt is not from an impact at all, but a relic of the way the planet accreted its material, a sign of asymmetric growth in a turbulent, lopsided disk of debris. Each piece of evidence, from the chemical makeup to the orbital ballet of its moons, points to a formation history that was not just different but uniquely turbulent. Uranus is not a failed gas giant or a misplaced ice ball. It is likely a hybrid, a world whose very existence forces us to rewrite the story of our solar system's youth, a story where planets wandered, collided, and swapped places in a drama that left one forever spinning on its side. A single, fleeting glimpse is all we have ever had. For every mystery of Uranus, from its tilted heart to its diamond rain, our understanding rests on a foundation of profound ignorance, built from just a few days of close observation. The Voyager 2 flyby in 1986 was a monumental achievement, a snapshot snatched from the void, but it was exactly that, a snapshot. It showed us a world in its deep summer slumber, a single frame from an epic movie that lasts for centuries. To truly know Uranus, we must go back, and this time we must stay. The greatest unanswered question is not on the planet, but in our own ambition, the mystery of what we would find if we looked with modern eyes and patience. An orbiter circling the ice giant for years would transform every puzzle from a speculation into a map. It could trace the drunken wobble of the magnetic field through entire rotations, revealing the true structure of the dynamo deep within the supersonic slush. By measuring the planet's gravity and shape with exquisite precision, it could finally distinguish between the models, telling us if there is a distinct rocky core or a fuzzy gradient, and perhaps even detecting the layered accumulation of those diamond hailstones. It could turn its cameras on the fractured faces of Miranda and Ariel, mapping their canyons and plains to read their geological history like a book, and use spectrometers to sniff out the chemical composition of Oberon's dark stains or Titania's ancient cracks, searching for the organic building blocks of the early solar system. Most critically, an orbiter could be a climate observer across the decades. It could watch as the seasons slowly turn, monitoring how the atmosphere stores and releases solar energy, catching the birth and death of those ghostly dark spots, and measuring the faint whisper of the escaping hydrogen corona over time. This is not about filling in gaps, it is about discovering a world we have only dreamed of. Mission concepts have been studied for years, bearing names like Uranus Orbiter and Probe or the Uranus Pathfinder. These spacecraft, powered by nuclear batteries, would embark on a journey lasting over a decade to reach the ice giant. Once there, they would deploy a sturdy atmospheric probe to plunge through the blue haze, directly sampling the composition of the cloud decks during its descent, tasting the air of an alien world for the first time. The mothership would then spend years in orbit, a robotic sentinel patiently unraveling each secret. The data it returns would rewrite textbooks not just on Uranus but on the formation of all giant planets. It would tell us if our own solar system's architecture is typical or a strange outlier, and it would reveal the true nature of the most common class of planet we now find orbiting other stars, the ice giants. To launch such a mission is to choose wonder, to invest in a legacy of discovery that will echo for generations. The final, overarching mystery of Uranus, then, is the one we hold in our hands, the question of when we will decide to solve all the others. Uranus is a world built from contradictions. It is profoundly cold yet conceals a churning interior, featureless from a distance but scarred by storms that dwarf our planet, a silent giant that broadcasts a broken magnetic song. Every layer, from its hazy cyan veil to its hypothetical diamond heart, challenges our most basic assumptions about what a planet can be. This journey through 25 mysteries reveals not a bland outlier but a cosmic keystone. Its extreme tilt, missing heat, and fractured moons are not random flaws. They are interconnected clues to the violent, migratory adolescence of our entire solar system. To understand Uranus is to understand a different path of planetary birth, one where ice dominates gas and cataclysmic collisions were not exceptions but formative events. The ice giants, long overshadowed by their brilliant gas giant siblings, may in fact be the most common planets in the galaxy. By solving the puzzles of our own, we unlock a universal guidebook to worlds orbiting distant stars. So the next time you look up at the night sky, remember the sideways world. It is not a static blue marble, but a dynamic, evolving laboratory of extreme physics, holding secrets about our past and the fate of countless other systems. Which of its mysteries captivates you the most? Is it the diamond rain, the shattered face of Miranda, or the ghostly dark spots in its atmosphere? Let us know in the comments below. Stay curious and follow the latest news as scientists campaign to send an orbiter back to this enigmatic ice giant. For more deep dives into the universe's greatest puzzles, be sure to subscribe. The cosmos is stranger than we can imagine, and the story is